Today, we introduce IMU Tube, automatic extraction of virtual on-body accelerometry from video for human activity recognition. This work is done by Georgia Tech, UBCOM, CBA Lab, and Oxford Ox Analysis Lab, and my name is Hyuk Kwon. Wearable sensor dataset collection is difficult. User recruitment is expensive, annotation is time-consuming, and privacy or other practical reasons sometimes make recording impossible. Those challenges make a number of limitations in wearable datasets. Our benchmark datasets, such as Opportunity or PalmUp2, are small. They only have up to 20 plus participants, few tens of hours of recordings. Also, they are heavily label imbalanced. Opportunity dataset have over 70% of samples as null classes. Also, activity classes has not expanded much from the past. We're living in 2020, but we're still using benchmark dataset PalmUp2 from 2012, and the activity classes in PalmUp2 has not changed much from 2004. Those limitations make huge discrepancy between collected samples and the population dataset in the wild, and thus making limited room for improvements for deep learning. Human activity recognition didn't gain much from deep learning method. F1 score only had few improvements for opportunity datasets for past 7 years in deep learning era. Now that we looked into limitations in wearable dataset, let's see activity datasets in other communities. In computer vision community, they have massive labeled online human activity videos. Activity classes go up to hundreds and thousands, from everyday activity to sports, and each activity class have hundreds and thousands of video samples as well. Also, recent advances in computer vision technology enables motion tracking from video dataset. So here is our vision, IMU Tube. Online video repository has unlimited amount of human activity videos. Computer vision now enables full 3D human body tracking. If we can extract virtual IMU data from the videos, then we can build hard datasets with far greater breadth and width. Conventional wearable data collection happens in the lab. People do activity in the lab, and annotators observe and annotate. And such limited, small datasets are used for hard model training. IMUTube is different. We retrieve online videos and process 2D pose, 3D pose, and extract IMU from the on-body location. The large virtual IMU dataset from large video repository are now trained for hard model training. Here is an example of IMUTube dataset, 2 cyclists. IMUTube pipeline reconstructs full 3D motion for 2 cyclists and extract virtual sensor. The example shows right knee accelerometer from right-hand cyclist.
Hi, I'm Catherine Tong from Oxford, and now that we have introduced the IMU Tube pipeline, we want to ask, can we train hard models from virtual data? Now, to answer this question, we performed a set of extensive experiments evaluated on common hard benchmarks. Specifically, we extracted virtual data from videos coming from the real-world dataset, and we also curated a large-scale and the wild video dataset, including videos from YouTube. Our results are very promising. Here's a chart comparing the performance of a random forest trained on real data versus virtual data in 4 different scenarios, and we see clearly that their F1 scores are very comparable. Our results and experiments overwhelmingly support our thesis that IMUTube can generate virtual data that is useful for training hard models. Firstly, we show that we can learn capable hard models just from learning from virtual data alone. And secondly, we also see evidence that mixing virtual and real data for training can bring performance gains. Thirdly, We use transfer learning to extend our use cases to even more scenarios that are realistic, for example, when labels are missing. On the whole, we have shown that IMU Tube can be a viable method for the automated large-scale data collection for activity recognition, and thereby having the potential to extend this field to everyday complex activities and so many more opportunities. Our results are very promising, and we believe that a collective approach is the way forward. We therefore call out to different communities from computer vision, signal processing, and activity recognition to extend this work in the ways outlined in detail in our paper. We believe that this should lead to on-body sensor-based HAR becoming yet another success story. Here are our details, and we welcome you to contact us for a discussion. Thank you.